present today is a joint work done with Zhou from Fuji University, and um, it's about quantum simulation, which is considered one of the most promising applications for quantum computers. And this is identified as early as 40 years ago by Feynman. Um, and in particular, we're going to focus on analog quantum simulation. And normally when people think of quantum simulation, they typically think of digital simulation, which is reproducing the dynamics under Hamiltonian H by a quantum circuit. In contrast, analog simulation is the task of reproducing one quantum system H by another Hamiltonian H tilde, with the hope that H tilde is more easily accessible in the experiment. And also this idea of mapping between Hamiltonians is also very fundamental in the study of quantum complexity theory, since it is basically the generalization of mapping between constraint satisfaction problems. Now, in 2012, Serac and Zoller has argued that this type of analog simulation can be more robust against errors than digital simulation with circuits, because the errors that you encounter in these situations can be sort of treated as an effective temperature, which in any realistic physical system you want to simulate will also be at a finite temperature. And because of that, they're more promising to implement on near-term quantum devices. And indeed, there has been a lot of remarkable technological progress in this direction. I'll give you a couple of examples. So some of you may have heard about many-body localization and time crystals. So these are actually originally hypothetical phenomena proposed by some physicists. And there's actually been a lot of debate in the community about whether these are real effects or simply artifacts from finite-sized numerical simulations. And recently, in a series of beautiful experiments, mostly led by some of it led by Chris Monroe's group in Maryland using trapped ions, they were able to show that using 50 trapped ions, there's a lot of strong experimental evidence that these effects are real and they do exist in our world. And as another example, there also has been really cool developments in using systems of neutral atoms in rearrangeable optical tweezers to probe quantum phase transitions. And recently, coherent quantum phase transition has been observed in a system as large as 250 atoms, which is almost an order of magnitude larger than the state-of-the-art digital quantum computer. Analog simulators have also been proposed to address problems in chemistry, for example, using fermionic atoms in optical lattices. And there has also been some progress using superconductors to simulate vibrational spectra in molecules like ozone and water. So these are all very nice experimental, progress, which I hope help motivate why we care about analog simulation. But besides experiments, there also have been some recently nice progress in the theory of analog simulation. Specifically, it has been found by Cubitt, Montanaro, and Piddock in 2017 that there are actually some simple families of Hamiltonians that are universal in the sense that they can simulate all other Hamiltonians. So this means that a system as simple as, say, a 2D square lattice of qubits with, say, tunable Heisenberg-type interaction, you can use that to simulate something as complex as a long-range interacting many-body localized system, or a complex molecular Hamiltonian, or even the SYK model with all-to-all interactions, which is believed to model certain aspects of black holes. Now, this is nice because experimentalists often only have limited access to certain types of interactions and geometry in an actual quantum device. So if you can implement these universal systems in the experiment, you can in principle simulate anything you want. Well, this result is very nice, but in reality, we also care about the actual resources required using the simulators in practice. So in the analysis of this 2017 paper by Cubitt, Montanaro, and Piddock, they found that if you have a target Hamiltonian that is, say, two-dimensional, you can indeed efficiently simulate them on a 2D universal system. And by efficiency here, I mean that the number of particles required in the simulator, as well as all the interaction energy, aka the coupling strength between particles, they only grow polynomially as the original system size. On the other hand, if you have a target system that is, say, three-dimensional or worse, all-to-all connected, the analysis showing this 2017 paper showed that the interaction energy required to simulate them with a 2D system scales exponentially. So we call these systems which are, which may require exponential resource in some cases as weakly universal. So in my result with Doreen, we were happily able to show that there are in fact some very simple Hamiltonians that are strongly universal, in the sense that in addition to being at least weakly universal, all the resources required for simulation only scale polynomially for in the system size, as well as all the target precision parameters given. So this is in contrast to the exponential resource, required for some target Hamiltonians under weak universality. More concretely, this means that we're able to take any Hamiltonians, 3D or TR, doesn't matter. In fact, we were able to show that, as long as the Hamiltonian can be efficiently simulated by a circuit, which we call circuit simulable, we can actually map them efficiently to a 2D spin lattice model, or even a 1D chain of 8-dimensional particles. And so both of these families that I mentioned, 2D and 1D, are strongly universal in the sense I described. All the resources are polynomial, and this works for any target Hamiltonian that you can simulate with a circuit efficiently. So our result actually sort of established a complexity equivalence between analog and digital quantum simulation, since we have shown that a quantum system can be efficiently simulated by circuits if and only if it has an efficient analog simulation. And this actually implies that analog quantum simulation is perhaps realistic for more general systems than what was previously thought. Now, for the rest of my talk, I will first, define what I mean by Hamiltonian simulation and universality more precisely. And then I'll review the previous results about universal Hamiltonians, and also give you a more precise formulation of our results in how we constructed this strongly universal Hamiltonians. So let's start by rigorously define what we mean by Hamiltonian simulation. And what we did is we actually adopted a well-motivated definition, I think initially developed by Bravi and Hastings, but later refined by Cubitt, Montanaro, and Piddock. And the definition here is that we say that H tilde, the Hamiltonian, simulates the Hamiltonian H, if the following is true. So if you look at all the spectrum of your target Hamiltonian H, and if they are reproduced as the low energy spectrum of your simulator H tilde with some encoding V tilde that sort of preserves the locality of observables, then we say H tilde simulates H. More precisely, this means that the operator H tilde, when it's restricted to the eigenstates below some cutoff delta, that operator is epsilon close to the encoded original Hamiltonian H in the operator sense. And we also want the encoding V tilde to be approximately local in the sense that they are the isometry operator V tilde is eta close to the tensor product decomposition that acts independently on the original particles. And this locality is sort of important for preserving the locality of observables and noise processes, which is part of the argument why we consider analog simulations to be more robust in the experiment. And I want to then start, for my next definition, I will define universality, and we will define it in the context of families of Hamiltonians, which are two local. So we write basically any such two local Hamiltonian in the following form. You have a H tilde, which is written as a sum over some of the edges of an interaction graph. And the prefactor Jij, we call that the interaction energy. And H hat is the operator that acts on the side I and J. But in principle, this H hat could change between the different pairs of size. So we also inserted this site-dependent parameter phi ij. And so the idea of weak universality is that you can take any n particle reasonable Hamiltonian if you can map it to Hamiltonian H tilde from the family using the definition earlier that saying that H tilde simulate H. Then we say that this family of Hamiltonian is weakly universal. And we say that the family is strongly universal if it is both weakly universal and also that the Hamiltonian that you chose from the family H tilde all the energy and the number of particles only scale polynomially in the system size n, as well as all the precision parameters. So what I mean by reasonable here is sort of a little bit vague, but I will kind of tell you what I mean. So in the earlier work on universal Hamiltonians, the reasonable really just only refers to local Hamiltonians with the locality is constant. As we kind of develop our result, we find that actually this, a lot more Hamiltonians are can be considered reasonable. So the largest, reasonable families of Hamiltonian that you want to simulate are the ones that you can simulate with a quantum circuit, and that's what we call circuit simulable. And more precisely, we say that a Hamiltonian H is circuit simulable if there's a quantum circuit composed of, say 1 or 2 qubit universal gates. And if the size only scales, as long as the size of the circuit scales only polynomially in the system size, the time, as well as the precision parameter, and is able to approximate the evolution of the Hamiltonian for time t, then we say that this H is circuit simulable. Okay, so now I've sort of defined what universality means. I will also define translational invariance, because that's actually kind of a nice property to have, especially when we try to implement them in the experiment. So there's 2 notions of translation invariance, semi and full. So we say that the family of Hamiltonian is semi-translational invariant if all the 2 particle operators between every pairs of size that we have on the interaction graph is the same. So, for example, in the one I have drawn here, the example Hamiltonian H tilde here is semi-translational invariant because all the interaction is sort of XX form, even though the coefficient might be different. If we impose a stronger constraint that not only the operators are the same, but also the interaction energy is the same, then we say that the family is fully translational invariant. And note that here we only talk about the translational invariance of the Hamiltonian operators. We're not saying anything about the underlying interaction graph. But typically we consider sort of an interaction graph that is sort of regular, like a lattice, for this definition to make sense. Okay, so now I have defined, given all the definitions, so I can now describe our results in more detail. So I will start by, telling you a bit more about the previous results on universality. In this earlier result, they took basically any local Hamiltonian, it could be, say, a S by K model, and they apply a bunch of perturbative gadgets to them. So for example, you can take a complicated interaction graph and reduce the graph degree using something called the fork gadget. And it was also found later that you can make the gadget fit on the 2-dimensional lattice. So doing so allows you to map the original target Hamiltonian H to a 2D spin lattice model, as shown in the work by Pitog and Montanaro. And these models are semi-translation invariant because all the interaction operator between pairs of size are the same. In this case, it can choose them to be just Heisenberg sort of type interaction, while the interaction energy, Jij, varies spatially. Now, why are these Hamiltonians only weakly universal in the original construction? Well, that's because if you have a dense interaction graph like the SYK model, you need to apply degree reduction many times to map it to a finite dimensional lattice where the interaction graph has finite degree. And in general, you would need log n number of rounds of perturbative gadgets. And after each round of the gadget application, the interaction energy sort of blow up polynomially. And after log n number of rounds, you end up with the exponential overheading energy. And this is why in the original 2017 paper, they were only able to show that these 2D spin lattice models were weakly universal. But in our result, we were able to show that using better encodings, these very same spin lattice models in 2D are in fact strongly universal. And we took it a step further and showed that a very simple 1D Hamiltonian, where we only use nearest neighbor interaction on the line, where the particles have 8 levels, 8 dimensions. That Hamiltonian is also strongly universal. And here, the interaction between nearest neighbor enforces sort of transition rules between configurations in sort of a kind of a circuit computation. So there is sort of no translation invariance of any sense in this case. And as I said, both families of, are strongly universal, and they can efficiently simulate not only just local Hamiltonians, but any circuit simulable Hamiltonians. I will now compare our result to the previous result of not just the original 2017 paper, but also some follow-up work in this following table. So after the initial weak universality results in 2017, others have also been able to show that a bunch of other families in both 2D and 1D and actually possessing full translational invariance are also universal in the weak sense, because for all of them, the interaction energy in their construction scales exponentially in the general case, and in some cases, the particle number also scales exponentially. And in contrast, our results only require polynomial energy as well as particle number. And we were able to do this in both just a 2D sort of square lattice type geometry, as well as a 1D nearest neighbor line geometry. And I will make a couple of remarks here. So first, I will note that our results are somewhat tight because in an earlier work that I did with Dorit in 2018, we showed that general simulation of Hamiltonians with only sort of constant interaction energy and degree is impossible. So this basically means that it's unlikely that we're able to lower the interaction energy from polynomial to anything below. I mean, I guess there is possible room for a logarithmic energy, but certainly we cannot do it with constant energy. And secondly, I will note that the notion of strong universality is a strict subset of weak universality. And this is because there are weakly universal families like these two, which cannot be made strongly universal. And this can be seen via sort of an information theoretical argument because of the fact that these families have very strict form of translation invariance, where the only free parameter is the number of particles. Okay, so I will now, for the last part of my talk, I would describe sort of just the basic key ideas behind how we are able to construct our results. So the first idea is developing a method to perform degree reduction of interaction graphs in a non-perturbative way. Because remember from earlier, if you do degree reduction with just perturbative gadgets, you would generally require exponential energy if your starting degree is, say, order n. Another fact that I haven't that I mentioned just earlier is that we cannot hope to do degree reduction with only constant interaction energy due to this impossibility result. Nevertheless, we developed a way to perform degree reduction with only polynomial interaction energy, and this is done via circuits, which I will explain now. So the idea is to take any target Hamiltonian, which can be RTO interacting, doesn't matter. I have written it down here as a decomposition into eigenstates, but I don't need to know them explicitly. We can then consider the quantum phase estimation circuit running on the unitary e to the IH tau. So what this circuit does is that it takes any eigenstates of H as input and write down the energy eigenvalue as a bit string on some ancilla. So in the context of circuits, degree reduction is much easier to achieve than in the Hamiltonian context because we can use ancilla qubits and swap gates. And that's why we map the Hamiltonian to a circuit and then we do the degree reduction. And what I mean by that is if you take your circuit with some unitary acting on pairs of qubits, and we want to reduce the degree of each qubit, which in the context of circuits just correspond to how many gates are applied to them. And by simply adding ancilla gates, or fresh ancilla gates, in fact, after every gate, and then swapping the quantum state of the qubits that were acted onto the fresh ancilla, in this way, we can basically see that we are able to reduce the degree of the qubits A and B since they're never touched afterwards after the swap gates. So without much trouble, as you can see, we have reduced, the degree very simply using ancilla and swap once we converted the Hamiltonian to a circuit. We can also make this construction more sophisticated and create a circuit that's embeddable in 2D in a spatially sparse way. And then applying sort of something called the Kitaev circuit to Hamiltonian mapping allows us to transform this phase estimation circuit after the degree reduction step to a 2D Hamiltonian whose ground states encode the circuit computational history. But this trick on its own is not enough because we still need to be able to distinguish the eigenvalues between different eigenstates. And this can be done via a second idea, which is making use of the fact that, in the phase estimation circuit, the energy is written down as a bit string on the ancilla at one point. So then by adding the energy penalty term to the Hamiltonian bit by bit, so once you have your energy written down as a bit string, you can simply, add a penalty to that particular bit, well, and also, time it so that, it only applies when the circuit has run to the point where the energy is written down. Then, using this very simple energy penalty term, you can basically recover all the eigenvalue structure of the original Hamiltonian. So using these sort of two key ideas, we're able to basically take any circuit simulable Hamiltonian, which, as long as you have an efficient circuit for the e to the IHC, you can then, using very standard techniques like, trauterization, et cetera, and map it to a phase estimation circuit using only nearest neighbor gates in 1D. And then you can use sort of this non-perturbative degree reduction and the energy penalty to, map the circuit to a 2D spatially sparse circuit, and then that could be mapped to a 2D spatially sparse Hamiltonian, which then using, additional ideas like, these gadgets that are embeddable in 2 dimensions, we can map it to a 2-dimensional semi-translationally invariant Hamiltonian on say, a square lattice. And for the 1D construction, it's sort of, very similar. We can take the phase estimation circuit in 1D, and then we can sort of modify the 1D clock Hamiltonian construction that was used to prove QMA completeness of 1D Hamiltonians in papers like the 2007 paper by Dorit and others, as well as a more refined construction later by Halgren, Nagai, and Narayanaswamy. And you can actually, use only 8-dimensional particles in 1D to sort of map this circuit to a Hamiltonian where all the low energy states reproduces the original target Hamiltonian's eigenstates. So that's basically the outline of the structure of our construction, and that's what enabled us to get this nice strong universality results. I will then end my talk now with a summary of what we've done. We have established that the strongly universal analog quantum simulation is possible, not only for local Hamiltonians, but actually for any circuit simulable Hamiltonians. And this can be done, as I said earlier, that can do it with something as simple as 1D, 2D kind of lattice models using only polynomial number of particles and interaction energy. And we believe that this result is somewhat tight, at least in the asymptotic sense, because there's no way to lower the interaction energy to constant by an earlier impossibility result. And our result has established sort of this equivalence between the being able to do efficient circuit simulation and being able to do efficient analog simulation. And really, the takeaway message is that I think that analog quantum simulation really is more relevant for many more systems than what was maybe previously thought. And there are also some very I think interesting open questions that we would like to pursue. In particular, we're interested in to understand if we can improve the translation invariance properties of our construction and potentially extend them to fermion-based simulators. And furthermore, in our work, we did not really use the most efficient construction and really chose the methods that are most straightforward for provable results. So there's a lot of room for improvement to bring the overhead down to an experimentally relevant regimes. And in particular, we were wondering if there's a way to develop sort of the kind of a way to do degree reduction locally beyond just sort of this Hamiltonian to circuit to Hamiltonian idea that we have. And lastly, we want to develop a better theory of noise in these analog simulations, because most of our current understanding is based on sort of heuristic arguments and folklore. And in conclusion, I hope I have convinced you that the future of analog quantum simulation is bright. And I invite all of you to try to work on these questions with us. And I'm happy to take any questions from the audience.
Thank you very much, Leo.
I have a question, Leo. You know, that's a very nice result, but there's a different way one could ask these same questions in terms of saying, well, how would you program using Hamiltonians? And so if you look at it from that viewpoint, then what you're saying is, well, you program using Hamiltonians by first converting to circuits and then programming the circuits. But could you look inside your results and say, now that you have your result, could you directly program in terms of Hamiltonians, and what would those primitives look like if you take it apart?
Yeah, that's sort of what I'm kind of alluding to here, because, you know, I think that it is unsatisfying to kind of go through circuits in order to make our result work. And I agree that, now that we know that it is possible to do this sort of degree reduction, to do this efficient mapping, at least in principle, there are probably smarter ways to do it. And I think that, especially often what happens is that, if you have a particular Hamiltonian in mind, and you have a particular experimental system in mind, there's often, efficient ways to map between them, from a more, like quantum optics point of view, for example, there are tricks one can play to engineer specific kind of type of interactions. So that is something that we are thinking about. But yeah, we don't have any, concrete results yet, but I do believe that, there's probably a way to do this without going through circuits.
Thanks.
Following up on Umesh's question, it also occurs to me that the sense of time is different between the original Hamiltonian and the final one, because in the final one, time is the time through the circuit elements. And that notion of time is enforced by the clock that's used to represent the sequence of gate operations. And so it becomes nonlinear with respect to the original time. Am I correct about this? And
in some way, yes, but I think there's a distinction between, so the time that's in the circuit, really, is applicable to sort of the precision of the sort of the eigenvalues that you want to so basically the time that you use in this virtual circuit that you use in this construction really is related to how precise you want your final target, final Hamiltonian to be in terms of the eigenvalue, how close they are to the original eigenvalues. But that is also important if you want to, say, simulate the original Hamiltonian to some time, because you need your eigenvalues to be precise if you want to reproduce the full dynamics to some given time. But they're not, directly related, but they are related in this sort of roundabout way, if that makes sense.
Yeah, I appreciate the roundabout connection, but if I were just speaking as an experimentalist, for original system, often experimentalists want to measure some observable as a function of time. Mm-hmm. And then if you go through the circuit representation, you'd have to do something else to get the same observable as a function of time, because now the increase in time will be only an increase in the first part of the phase estimation circuit, and you still have to do the sequencing through your Fourier transform, et cetera, et cetera.
I think that, it's possible that, often in the experiment, you don't necessarily also care about, reproducing the full spectrum precisely. There's probably, often when you measure things in the experiment, you maybe only care about, certain properties that are robust, that are maybe universal, I'm using universal here in a different sense, in more condensed matter theory perspective. But what I'm saying is that, it's possible that you don't actually need to have a very precise error in the eigenvalue mapping to get a good, to simulate long time kind of, observables, because maybe they correspond to low energy physics that is robust.
That's fair. Thank you. Other questions? If not, I have one more.
How about a question about, is there like an easy intuition for this possibility of constant strength degree reduction?
Yes. So basically, what we did, in the earlier work is that we were able to find some counterexample that we can construct, where basically the idea is that we constructed some Hamiltonians which are all interacting, so they have a dense interaction graph, and we're able to make it so that the ground state is sort of this highly entangled state that basically between any pairs of particle there is sort of some non-trivial entanglement. And also we make that ground state gapped. Now, some of you may know that gap Hamiltonian in sort of a finite dimensional lattice, for example, necessarily have sort of this exponential decay of correlation. So basically, that means that if you map that Hamiltonian that's dense to a finite dimensional lattice, for example, you cannot reproduce sort of this strong correlation between every pairs of particles, because necessarily there exists particles that are far apart once you map it to the finite dimensional lattice. Does that hopefully?
Yeah, that helps a lot. Thanks.
Okay.
Yeah, so I have a question. So you're measuring the cost of the simulation by the blow up in the coefficients.
Mm-hmm.
What's your cost in terms of the increase in number of particles? And is there room? Is that polynomial?
That is also polynomial. Yeah, like everything, basically the spectral norm of the simulator, the whole operator is polynomial. So it's all the particles, like the number of particles is polynomial, the interaction energy of every term is polynomial.
So is there hope of decreasing that, or is there an impossibility result related to that? So could you potentially get O of 1 blow up in the number of particles?
I guess we haven't ruled that out yet. I guess maybe, I don't think necessarily we can rule that out. I mean, it's very possible that only a linear scaling is necessary for the number of particles in the simulator, but we haven't really studied that particular direction, I guess.
The last two questions were really very much along the same lines as the no fast forwarding theorem that applies for digital quantum simulation. I'm curious if you have thought about relating that, because, for example, maybe you'd like to be able to fast forward some simulations also. And if you can fast forward in an analog simulation because you know the mean field Hamiltonian, surely you should be able to fast forward your simulation as well.
Yeah, that's a very good question. Yeah, that is an idea we've thought about. Like, I think that the connection that we had in mind is that I think certain fast forwardable Hamiltonians have probably can be simulated more easily. Like, for example, they could even be simulated efficiently by a fully translational invariant one. But I think the no fast forwarding essentially, we were trying to basically prove that there's no way to have a strong universal Hamiltonian with full translational invariance. And I think we might need to rely on no fast forwarding.
I would like the reverse. And I would also like to see somebody postulate a no squashable theorem. So like the last two questions we're asking, can't reduce space as well. And then for you to come up with some squashable simulations because you know something extra about the system.
That's a very cool question. That is a very cool direction. Yeah. Thanks for that suggestion. Yeah, that's very cool.
Other questions? We still have a few minutes, I think, because the schedule officially said 1:15. I do have another question if nobody else does.
I think there's some questions in the Q&A.
Oh, good. Thank you. Okay. Forgive me for not seeing those. Okay, so your definition of what it means for a Hamiltonian to simulate another involved locality of the encoding isometry. Your definition of what it means for a Hamiltonian to simulate another involved locality of the encoding isometry. How do I see that that's true when you plug things into the clock construction?
Yeah, that's a very good question. So that's kind of one of the things that we have to deal with to make sure that you satisfy this local like this locality, and the idea is basically uh, uh, there's sort of twofold. First of all, we sort of we have the circuit that runs the quantum phase estimation, and we actually uncompute it so that we get back the original eigenstates where they're not really entangled with all the clock degrees of freedom, and then we also idle it for a long time after the uncomputation, so that basically the history state of this circuit is essentially just the original state, weakly entangled with some clock qubits, and 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 basically, in the idling part, crucially, we do not move the state of the particles around in the lattice. So basically, there's a long, part of the history where the eigenstates sit basically locally on some subset of the particles, and because of the fact that they're only weakly entangled with the rest, this locality condition in the definition is satisfied approximately, which is all you need. I hope that answers the question. If not, I can elaborate more.
Okay, and another one. Could you give an example of a strongly universal experimental analog Hamiltonian system?
Yeah, so I think, for example, the IBM device implements essentially the XY interaction on a 2D lattice, and that is an example of a strongly universal Hamiltonian. And I'm sure that many systems like in code atoms, ions. I mean, I think they don't necessarily. I mean, in ions, I think that also the XY interaction comes for free. But I think you can use techniques like like dynamical like kind of decoupling to kind of, or like dynamical Hamiltonian engineering to sort of use pulses to effectively shape turn like an Ising type interaction, for example, into an XY or maybe even Heisenberg. So I mean, so the only thing that I think that I know of that comes naturally is as an XY, I think is the IBM device. But then again, I think actually a lot of Hamiltonians beyond the Heisenberg and the XY are strongly universal. In fact, we showed that this is actually based on the work with Qubit, Montanaro, and Piddock. They were able to show that basically most two qubit interaction, except for basically almost a measured zero set, is like strongly universal. But the mapping is sort of non-trivial. That's probably the hardest part.
Also, isn't the overhead non-trivial? So you need a very, very, very big IBM quantum computer to be universal.
Yeah, I mean, yes, all of the overhead is non-trivial currently. They're polynomial in principle, but they are just n to the 20 or something like that. But I believe that all of these constructions can be improved much further.
Right.
Just one follow up, Leo. I now feel that I'm not really sure about what your notion of locality was. Can you just go over that briefly?
Yeah. So my notion of locality here, which is adopted from the definition from the 2017 paper, is basically the eigenstates. There are eigenstates of the original Hamiltonian, and there are eigenstates of the Hamiltonian H tilde, and they're mapped by this isometry V tilde. And I say that this mapping, this encoding is local if V tilde can be approximately decomposed into a tensor product that acts independently on each of the original particle. So it's not exact, so that's why you could allow sort of weak entanglement between the map particle with the clock qubits, for example.
And you want that for the lower part of the spectrum.
This is only necessary for the lower part, like the part of the spectrum of H tilde that simulates the spectrum of H.
Good, Imesh. Are you happy?
Yeah, great, thanks.
Of course, you're always happy. So we can move on to another Q&A. Are there known examples of non-circuit simulable Hamiltonians?
I think, like, if you have a Hamiltonian that is like literally a random Hermitian operator in this exponential size Hilbert space, that's probably not simulable, just because the complexity of describing it is exponential. That's like a very trivial example that I can come up with on the spot. But other than that, I'm not sure. I mean, maybe most of the Hamiltonians that one encounter in nature, I think, are circuit simulable, I think.
I think that's a good answer. Let me take privilege as chair to ask one last question, which I'm burning to ask, which is, you're constructing really just shows you can do a Hamiltonian simulation of a particular class of phase estimation circuits. But that phase estimation circuit could be very, very universal. It could, for example, be singular value transforms, signal processing. It could actually be not doing a Hamiltonian simulation. So you're just showing in many ways, if I understand right, that you can efficiently do analog simulations of lots of digital quantum circuits.
Yes.
So how about a universal quantum analog machine, since you can use singular value transforms?
That is a very tempting idea, but I will say maybe that, one caveat is that, in this digital circuit that really correspond to actual algorithms you want to run, you do care about the fidelity of the final state. Whereas in simulation, we don't necessarily care about, having all the states being exactly reproduced to some epsilon. All we care about are, local observables, and even if there's some finite temperature, that's okay. So I think, yes, in principle, you can implement those, quantum singular value transform circuits, these algorithms as an analog simulator, but you might get a result that's not what you wanted, is when you measure it, at least.
But most of these digital circuits have digital outputs. And if you're doing something that's strongly distinguishable, like classification, or in QSVT, sometimes just that one qubit is the most important single qubit. So maybe it's fine for your construction.
I see. Yeah, that's true. Yeah, maybe there's a way to, leverage the robustness of this analog simulation to implement some of these algorithms. Yeah, I mean, that would be very cool. I think I need to think about it a bit more.
Wow. And then you can write a paper that's about the grand unification of everything quantum. Okay. Let's thank Leo Zhou for a beautiful talk.
Thank you.
And next up, we have Zivka. Yes?
Yes.
You said hello. Okay.
Hey, how do I share my screen?
Go ahead and share your screen. Zivka is from the Weizmann Institute of Science, and we'll